Good morning, students. I hope you all are well. We are doing vector spaces. Today, we will consider the example of vector space but in different way. We will discuss the geometry of the given set, which is a vector space, and we will try to develop one more part that is related to vector space. So let us continue. This is the set of ordered pairs this is r square. R square as usual, that is r cross r, and we know that this is a vector space. This is a vector space over R with the standard, or I say regular, addition and scalar multiplication. That means B cross B to V such that and let F is R, field is R such that image of this for all A belongs to R, for all L belongs to V. Way is given by this. Actually, it is xy plane. See the geometry. All the points are lying in xy plane. You can see. This is the set of ordered pairs. This is a vector space over R with the standard or regular additions and scalar multiplications. This is the closure property of addition. This is the closure property of scalar multiplication. Then remaining 8 properties be verified. So this is a standard example. Maybe it is r cube, then we write x comma y comma z and so on. So if this one is given, that means if we consider any 2 points, suppose I say let 1 comma 4 belongs to V. Then Regular addition means component wise addition. So it is 1 plus 5, that is 4 plus 2, that is 6 comma 6. Here we are getting this. And this is also, if I consider suppose minus 2 belongs to R, then minus 2, alpha suppose I say 1 comma 4 for example, then what will happen? It is minus 2 minus 8. Now what is the geometry behind it? Let us say. This is xy plane. Every point lines plane with a member of this V. 1 comma 4 1 comma 4 is the point. Here it is. This is 1 comma 4. Then 5 comma 2, 1, 2, 3, 4, 5 and 2 units here. Let us suppose this is the point A and this is the point, I say it is B, that is 5 comma 2. I join this one. Similarly, I join this. If I consider this way, then you see OA, this is the position vector of A, that is 1 comma 2. Suppose this is alpha, say. And OB, you know that vector algebra, position vector of point B, that is 5 comma 2, and this is beta, for example. So if we add alpha plus beta, then we find we are adding these two, OA plus OB, and these two vectors are added with the help of law of parallelogram. Okay, so let us complete the parallelogram. Suppose this point is C, for example. So here is the diagonal. So vector OA plus OB equals to OA and plus OB. OB is equal to AC. And this is OC. That means position vector of C. And if you find the position of this one, you will say that it is 6. And this side you find also 6. This is 6 comma 6. Position vector of C, that is 6 comma 6. So actually we are adding component wise, it means we are adding the position vectors. You can consider any point or any 2 points or 3 points, then you can think about it. So It is also true in 3-dimensional, it is also true in n-dimensional, it is true in 2-dimensional and 1-dimensional also. I will consider that also. Now second one, if I consider this one, that is 1, 4, point 1, 4 is this. One comma 4, 1, 2, 3, 4, 1, 4. Yes, so it is minus 2, then it is minus 8. So 1, 4, here it is wrong, it is not 1, 2, it is 1, 4. Writing mistake it is. Yes, 1, 2, 3, 4. It's 1, 4. Yes. Minus 2 is a number, that is a scalar number. 1, 4, this is a point. So if we multiply this one, then it is a scalar multiplication. Then it is minus 2, minus 8. Minus 2, minus 8 will be in the back, you can see. Down here. So it is, I just proceed it in the back. Find this. This is minus 2, minus 8. It is this vector. Okay, so whatever the operation is defined, that is the standard one here. So standard addition and scalar multiplication, that means we people are doing component wise. So if we perform component wise, that means it is nothing, we are using to add position vectors and scalar multiplication of this. Okay, now we come to the next part. So every point, whatever it is, with the help of this addition or scalar multiplication, we find the point in the xy plane. So these two operations are closed under the given. Okay. Now I consider the next one. Suppose W equals to look at this carefully. This is not equal to R square. Y coordinate is 0. X is variable, so it is entire x-axis. That means it is like this. Here W is subset of R square. Now the operation, you consider any 2 points. Suppose I consider one is this. Here it is 1. Second one I consider, see how to add. This is the yellow one. Suppose here it is. This is 3. So if I add, because we have to perform the point on x-axis only. So if I add this and this one, it is 1 unit, and this is 3 unit, 1, 2 and 3. So if I add this one and this one, then you see the answer. This part is added this way, so it is here you find this is the 4th part. So because it is in the same directions, so suppose I say it is A, this is B and this is C, so it is OA plus OB. is equal to, here it is OC, because line in the same line in the same direction. So if we add any two, the answer will be on x-axis only. And so here it is closed. Operation is closed. Similarly, if I multiply this by negative sign, then you find, suppose this white line, for example, 1, 2, and here it is 3. So this is minus 3. So if this is multiplied by minus 3, then again you will find a point on this line only. That means if we apply all the 10 axioms of vector space, you find all are satisfied. And if we look at geometrically, then we find that this is the subset of R square, and addition is closed, scalar multiplication is closed, 0 is the identity, and you just find the inverse of every member. The inverse of 1 is minus 1, inverse of 3 is minus 3, 1 by 2, then minus 1 by 2, and so on. So all these axioms are satisfied by this, so this is a vector space. I will just change this. Remember, here 0 is the additive identity. Okay, means 0, 0. Look at another example. You see, suppose let P equals to this is xy plane. This is the subset of this because it is x-axis. Your y coordinate is 0. Y is not given, so you can write x belongs to R. And similarly, here x belongs to R. So this is not equals to R square. You find P is a subset of R square. Look at the geometry. You people know that this is nothing. This is the line because y coordinate is fixed, that is 3. So it is 1, 2, and 3. You find this. If we consider 2 points here, this is 1, 0, this is 3, 0. If we add component wise, we find the answer is 4, 0. It is on the same line. Suppose I consider 2 points over it. One point is here, and other point is at this place. Suppose it is, fine, this point is 1, 3. And it is 1, 2, 3. Look at this point, and this point is 4, 3. These 2 points. So what is the position vector? Just like this. And it is this. Now if we add 2, then the answer is lying on x-axis. But if we add these one, suppose this is OA and here it is OB. This is OA plus OB. What is the answer? To add the position vectors, we have to perform the parallelogram. Here it is not possible because they are collinear, lying the same line. But here you can say and this point is suppose C. This is 5, 6. And this does not belong to P because it is above this one. Therefore, the addition is not closed. Addition is not closed. If you multiply this by some negative sign, then either it is up or down. Addition is not closed. So this is not a vector space. You remember, this is a vector space. W is a subset of this. P is the subset of this. So if W is a subset of this, it is not necessary that it is a subspace. May or may not be. If this is a subset of this one, and if this is a vector space, for example, then this is known as the subspace of this. And if we know that if it is a vector space, it means it must satisfy all 10 axioms, both closure properties and it. So you see the example. This is the vector space. These two are subsets of this one. This is entirely x-axis. This is parallel to x-axis. You can see 2 points you consider on this one, and if we add component wise, then it is not lying on this particular line because the y coordinate is fixed and here y coordinate is 6. So it is another part of it. So the operation is not closed. So it is not a vector space. And this is a vector space even then both are the subsets of R square. So if we want to prove a particular set given with the operations, then if it is a vector space, then it must satisfy all the 10 axioms under the given operations. If this is a subset and this itself is a vector space under the same operations, remember, under the same operations. Component wise addition, regular, component wise addition, regular, component wise scalar multiplication, component wise scalar multiplication. जो इसमें ऑपरेशंस है वो के वो ऑपरेशंस इसमें होने चाहिए, इनहेरिटेड, विरासत में मिले हुए. मैं वर्ड यूज करता हूँ विरासत. बाप दादाओं की जो संपत्ति है उसको विरासत में मिली हुई है, डीएनए उसका विरासत में है. तो जो ऑपरेशंस इसमें है उसी ऑपरेशन से ये चलेगा और वो यदि वेक्टर स्पेस बनता है तो ये इसका सब स्पेस कहलाएगा. So if this is a subset of this one and it is a vector space under the same operations defined on V, parental set, then W is called a subspace. Okay, but remember, to verify all the 10 axioms, it is time consuming method. So we will derive some particular property. Using that property, we will prove the given set is a subspace or not. Okay, so we will discuss this tomorrow, but today I would like to discuss one problem that is from the homework given to you. Suppose W is a non-empty subset of vector space V. W is a non-empty subset of vector space V. If W satisfies all 10 axioms of vector space under the operations defined on V, then W is called the subspace of V. This is the definition of subspace. W is a non-empty subset of vector space V. If W satisfies all 10 axioms of vector space under the operation defined on V, then W is called the subspace of V, otherwise not. Tomorrow we will discuss how to prove a given set which is a subset of the vector space as a subspace without using all the 10 properties. Okay, so this is that. Now, yesterday, if you remember, you were given one question on it. The homework question. One of the students asked me, and she wrote the answer, but it was written wrong. The question was, I hope the set is cos t, sin t, and t belongs to R. Yes. Such that cos t1, sin t1, cos t2 equals to remember, it is not component wise. Okay, so be careful. And scalar multiplication, I hope it was cos ct sin c. Additive inverse, identity, and additive inverse. And we have to verify that this V is a vector space. Okay, fine. One of the students has simplified this question and wrote the additive identity like this. And the inverse as yes, I remember Purvi. Purvi is one of the students, and she wrote the answer like this. Then I replied, whatever you have written, I am saying whatever you have written is wrong. Then she wrote the answer as this is 1, 0, and this one is cos t, minus sin t. Then again I told her, pay your proper attention and find it out. Remember, in your mind, whenever you simplify, the answer is correct. But when you write this one, you write in the wrong manner. Remember, the elements are given in this format. This is a column matrix. Again, I am telling you, this is a column matrix. And if you write like this, then this is the closed interval. This is not a column matrix. Even if you remove this one, then it will be a row matrix. So this is wrong. Again, this is the wrong. So what is the correct answer? Additive identity is cos 0 sin 0. That means you can write just like this. I hope you have understood. Cos of this is cos t, and this is minus sin t. This part, whatever is, this is wrong, and this is also wrong, because it looks like the interval, and whatever the interval is also wrong. Okay, so be careful which type of elements are given, so you write the answer in that particular format. Okay, so thank you very much. If you have difficulty, you write the comments in the comment box. God bless you.